Imagine drawing a coastline across a map. Not a rough sketch, a real shoreline. The place where land ends and water begins. Now imagine following that line for thousands of miles, only to discover it climbs uphill, drops downhill, and rises again. Not by a few feet, by distances large enough that no ocean on Earth could ever behave that way. Either it is not a coastline, or the world itself changed after the coastline formed. That possibility begins on Mars. Spread across the planet's northern hemisphere is a vast region of low terrain. On topographic maps, it appears almost like a giant basin. South of it, the ground rises into older, higher landscapes. Between them sits a boundary that caught the attention of planetary scientists decades ago. On a map, the feature looks strangely familiar. It traces the edge of the northern lowlands. It loops around the basin the way ancient coastlines wrap around seas. Seen from above, it resembles the outline of a vanished ocean. The image creates an immediate temptation. If Mars once had abundant water, perhaps this line marks the place where an ancient sea met the shore. The idea seemed reasonable. Mars preserves river valleys. It preserves flood channels. It preserves evidence that liquid water once moved across its surface. A northern ocean offered an elegant explanation. Water flowing downhill would naturally collect in the lowest regions of the planet. And the northern lowlands are exactly where that water should go. The map appeared to fit. As more data arrived, the picture became stronger. Improved surveys traced possible shoreline candidates around enormous portions of the northern hemisphere. Researchers compared boundaries, contacts, and landforms. Again and again, the same impression emerged. The pattern was difficult to ignore. A coastline does not have to announce itself with waves frozen in stone. Sometimes it survives as a subtle boundary, visible only from orbit. Sometimes its significance emerges only when viewed at planetary scale. Mars seemed to possess exactly that kind of evidence. The more complete the maps became, the larger the proposed ocean appeared. And the larger it appeared, the more confidence the idea inspired.
We can observe the precise
Then scientists performed the test that every coastline must pass. They measured its elevation. On Earth, an ocean surface follows gravity. Water settles into an equipotential surface. Local conditions can create small variations, but coastlines remain fundamentally level. That is what makes them coastlines. The Martian boundary should have behaved the same way. Instead, the measurements produced something deeply uncomfortable. Different sections of the proposed shoreline occupied dramatically different heights. On a color-coded topographic map, the contradiction became impossible to miss. The same line crossed regions separated by enormous elevation differences. A shoreline that appeared convincing from above suddenly looked impossible when viewed through the lens of gravity. The image did not disappear. The pattern remained. But its meaning changed. The map that seemed to support an ocean was now undermining one. If the line truly represented an ancient shoreline, the water would have needed to flow uphill. If the water obeyed gravity, the line should not exist in its observed form. The strongest piece of evidence had become evidence against itself. Researchers searched for ways to absorb the contradiction. Perhaps the mapping was wrong. Perhaps separate features had been connected incorrectly. Perhaps the proposed shoreline was not a shoreline at all, but something else entirely. These possibilities carried weight because the elevation problem was not a minor detail. It struck at the heart of the interpretation. Yet another problem emerged. The pattern remained remarkably coherent. Even critics of the ocean hypothesis faced an awkward reality. The boundary continued to resemble exactly the kind of feature many researchers would expect from an ancient sea. Rejecting it entirely felt unsatisfying. Accepting it felt impossible. The story entered an unusual state. The evidence refused to disappear. The explanation refused to work. Each return to the map produced the same experience. Confidence would rise as the boundary wrapped around the lowlands. Then confidence would collapse when the elevations appeared. The shoreline survived. The simple shoreline explanation did not. That forced attention toward a different possibility. What if the coastline formed correctly? What if the water really had obeyed gravity? What if the problem was not the ocean? What if the problem was Mars? Viewed from space, Mars is not a perfectly static world. One feature dominates the planet like a geological monument. The Tharsis region, a colossal volcanic province stretching across a vast portion of the planet. Its immense mass altered Mars on a global scale, not simply through eruptions, but through weight. Planets respond to weight. Over immense spans of time, the distribution of mass can influence how a world is oriented relative to its rotation. The concept is known as true polar wander. The phrase sounds dramatic, but the idea is surprisingly physical. Imagine placing a heavy object onto a spinning body. Over time, the body may reorient itself into a more stable configuration. Not a sudden flip. Not a catastrophic tumble. A gradual planetary adjustment. Applied to Mars, the implications were extraordinary. Suppose an ocean shoreline formed when the planet occupied a different orientation. Suppose the water settled exactly as water should. Then suppose the planet's outer shell slowly shifted relative to its spin axis. The coastline would no longer appear level today. Its geometry would become distorted. The waterline would remain preserved. The planet beneath it would have changed. Suddenly, the contradiction transformed. The elevation differences no longer acted solely as evidence against the shoreline. They became potential evidence of something larger. Planetary change. The shoreline and the contradiction could survive together. Not because gravity had failed. Because the surface recording that ancient water was no longer arranged exactly as it had been when the water existed. The idea remains debated. The proposed shorelines are not universally accepted as confirmed coastlines. The existence, size, and history of a northern Martian ocean remain active scientific questions. And true polar wander is not a final answer stamped onto the planet's history. But something important happened when the contradiction appeared. The mystery changed. At the beginning, the map seemed to ask a simple question.
From this vantage point,
did Mars once have an ocean? By the end, the map was asking something larger. How much of Mars changed after that ancient chapter ended? Return now to the original image. The boundary surrounding the northern lowlands. At first glance, it looks like evidence of water. Then it becomes evidence of a problem. Then evidence against a simple explanation. And finally, something else entirely. A possible record of a world that did not remain fixed. A coastline that may preserve not only the memory of an ancient sea, but the memory of a planet reshaping itself long after the water was gone. The line never changed. Only our understanding of what it might be showing